Elasticsearch. Everyone here knows what is it, right? But how do you use it? Let's do a quick warm-up after the lunch. Please raise your hand if you use Elasticsearch for full text search. Oh, nice. And for maybe machine learning? Anyone? Okay. And for logs and event analysis? Oh, thank you. Nice to see so many hands here. Actually, there are many options how we can use Elasticsearch. So our use cases may really differ. However, I bet everyone here thought at least once about how to make it faster. Hello? Sorry. My name is Maria Telman. I'm Java developer and my team technical lead at Outbrain. Outbrain is all about content recommendations. Monthly, we generate more than 300 billion recommendations to 1 billion readers across thousands of websites. You've likely seen our widgets like this one, offering ads on read next suggestions. I'm from the read next side. Our service handles up to 3 million requests per minute at sub 10 millisecond average latency. And to answer them, we fetch almost 500 million items from our Elasticsearch. And today, I'll share with you how we boost our Elasticsearch performance by optimizing the cluster, search request, search response, and writes operation. But before starting, a couple of words about our Elasticsearch setup. It keeps metadata of web pages like articles, blogs, news posts, and more. And we use Elastic to select a few hundred best items for every request. We update a lot, but our goal is to nail search performance. We are running on Elasticsearch 7.17 with Java API client on the service side. And now, we need to get started. Cheers! Okay, so what is the first step to optimize any search? To optimize the search area for sure, let's briefly recall how search works in the context of the Elasticsearch cluster. The cluster is a collection of nodes. And every node, just an instance of Elasticsearch, these nodes hold one or more indexes, where index is our database, the place where we keep our items called documents. An index is split into one or more pieces called shards. Now, every shard is a standalone chunk of data, living its own life and having its own doppelgangers, called replicas. And when our client sends a search request, it can reach any of the known nodes, but this node doesn't answer immediately. Instead, it becomes a coordinating node for this request and sends new parallel requests to other nodes. And then, within each shard, search is executed in one single thread sequentially. So, we face here two clear constraints. First, shards should be small, officially up to 200 million documents, but the fewer the better. Second, distributed search incurs overheads like node hopping, and we would like to minimize the number of shards too. Ideally, if we put everything into one shard, we could skip the coordinating node and get responses immediately. But to put all into one shard, not that simple. You know, millions of web pages are published every day. At Outbrain, we've learned about almost 18 billion documents, too many for one single shard. Luckily, after some analysis, we agreed that not all data is essential, and many web pages go stale in hours. So, we implemented a pre-selection flow that throws away all unused content, slimming our inventory down to just 8 million. Yes, that was a true game changer. And now we've got one shot, tons of replicas, and we can set preference local to disable the coordinating node. But are we all set? Not so fast. Since version 6.1, the coordinating node acts as an adaptive load balancer. Every node monitors all other nodes' health status and selects the less busy ones when sending requests. Our client isn't that smart. It just takes turns sending requests to every node it knows, even the slow ones, until it hit timeout. Not very good. To avoid such hiccups, we need to implement an adaptive replica selector on our side. For that, we use the Elasticsearch sniffer library. Once activated, the sniffer periodically grabs a list of all active nodes from the cluster and updates the REST client with this. And we can customize which nodes are selected here by providing our own implementation of the node sniffer interface. And from there, it's on us to monitor all node status and select the best nodes. So, to optimize a search area, we should minimize the document count. Skip coordinating node if we have just one shot. And enable sniffer. It makes sense in any case. Our next step is to simplify the search itself. Here we implemented some basic optimizations that are pretty common. First off, we avoid heavy queries like full-text search. All heavy lifting should be done beforehand, and during real-time search, we just use term-level queries to get exactly what we need. Next up, sure, we use filters. You know, the search request can include filters in either the filter or query context. And filters are much faster because Elasticsearch might cache them and doesn't calculate scoring for them. We use filters exclusively. And that brings me to the next question. How do we score documents? You know, by default, Elastic ranks documents by their relevance. But that's not what matters to us. Our focus is popularity. So we need our own scoring. Something flexible. You know, there are different views on what's popular, and we need to implement several of them. So we started with the most adaptable tool we've got, scripts. Yeah, scripts may be very sluggish if we put them right in the search request. Instead, we implemented them as Java plugins. Elasticsearch allows us to load such plugins directly into Elasticsearch memory, and that's way faster. With these plugins, we could do everything we wanted to. Mix different fields, tweak calculations on the fly, and more and more and more. All good, right? Well, almost. Maintaining these plugins was a real challenge. Forget about running end-to-end automatic test or debugging. Every time we launched a new plugin, we needed our DBA in the loop. If a plugin had a bug, so we choose a different path. And now we pre-calculate the scoring and store it as a field in Elasticsearch, or actually different fields to cover different approaches to popularity. And now the big question is how to rank documents in Elasticsearch by a specific field. There are several options, and we've tried out 3 of them. The first and the most obvious is to sort documents by this field. Simple and very efficient. We kept using it for quite a while. We also experimented with field value factor. You know, you can use it in the search request to adjust or replace the original scoring. Sounds good. However, based on our experience, it turned out to be slower than sample sorting, so we decided to pass on it. Next, we tried rank feature, introduced in Elastic 7.0. Now, in our mapping, we define our popularity field as a rank feature, and then we can use it in the search request in the query context. And yeah, remember to disable track total hits. This small change surprisingly enables another feature, early termination. And now, if we need the top 100 documents, Elastic won't retrieve more than 100 documents from each segment. That is nice additional optimization. So we ran our tests and saw 40% drop in the latency. Amazing, isn't it? Yes, it looks like rank feature is a real game changer here. And now let's move to another search optimization, index sorting. Seems straightforward, right? We can set up our index to store documents in a specific order originally. And then on retrieval, Elasticsearch just takes the top documents without actually sorting them. That's nice, especially if we enable early termination. However, there are two issues here, right? First, to enjoy this, we need to use sorting. And we agreed that we don't. Second, you can set only one index sorting configuration per index. And what if you've got various ranking strategies, like we do? Then you can speed up queries. It said that index sorting places documents with similar values together, helping Elasticsearch in bypassing unneeded data during complex queries with conjunctions. That's the theory. Honestly, we were really skeptical it could work in our case with our different filters that are often optional. Yet we decided to give it a shot, and our average latency dropped by half when we applied index sorting to just one filter. Let's summarize. To optimize search requests, we should use light queries and filters. If the relevance score is relevant for you, go for it. But if not, sort will work better than any script, and rank feature is the best. And go for index sorting always. Okay, we've optimized one part of our search, how to find the items, and now the next part is how to fetch them. There's a bunch of ways to get documents data from Elasticsearch, and 3 of them are based on the same stored field storage. This storage looks like an array of rows with direct access to each document. However, data inside document is kept as a linked list of fields with sequential access. Now, our first and default option to get data is source. Source is just a JSON that we send to Elasticsearch when indexing our document. And now Elasticsearch keeps this as a large binary blob here in the second cell. Everything, including fields. So to return the source, Elastic has to load this entire blob, convert it, transmit it, then our client parses each field. And what if we don't need all this field? And usually we don't. Then we can fetch selected fields using fields or source filtering options in our search request. However, but these options are based on the same source. So Elasticsearch still needs to load this entire blob, convert it, parse it to find the required fields. Not so good. The next option is stored fields. They are kept separately here after the source, and that's great. But this is a linked list. So to read the last field, we must paginate through all the fields before it, including source if we keep it. No worries, stored fields are disabled by default, and I don't think we want to enable it because there's a better option to get partial data, doc values. They have their own storage, and it's columnar and nicely optimized. It sits off heap on disk, so to be efficient, it requires SSD. Now, in our search request, we specify the doc values we need, and then Elasticsearch fetches only those. No messing with source or stored field storage, no extra parsing. Nice, right? Yet doc values do have their own overheads. Look at this graph from Ella Porciani. It fairly illustrates how fetching more fields affects latency. The green line here is for source, and the orange one is for doc values. You see, the doc values latency shoots up when we get more and more data, and in these cases, source will be more optimal. However, if our aim is speed, we should select the bottom left corner here. That means using doc values to get ideally just one field ID. But well, usually we need more details about items, right? And it seems handy to use Elasticsearch, but as a search engine and data store, and to get everything with one request. We also did it for years. However, there are better options to get data per ID. Today, we use a combination of caches, and here you can see how that improved our service performance. On the left side here is our old approach with just one query to Elasticsearch, and on the right side, new approach including cache calls, and they are together much, much faster than just one Elasticsearch call. So, doc values. Unfortunately, our new Java API client is designed for source. If we don't get it, things can get tricky and unstable, so be cautious with doc values. And if you are still on Elasticsearch 7, check out this issue and the workaround for this, but I won't expand on this right now. Okay, can we reduce the size even more? We agreed not to enable stored fields, yet every search response still contains them. Luckily not source if it's disabled. So which other stored field are we always getting from Elasticsearch? Any guesses? Remember the slide? ID. We always have ID. This is Elasticsearch's internal ID. You can put here your own entity ID if it's suitable. Not any ID is good for Elasticsearch. But in any case, retrieving it costs how much? Good question. We tried disabling it by adding a magic word none to the stored fields parameters, and here's our results. You see, just fetching these IDs cost us almost 10% of our average latency. So we decided to disable it, and unfortunately, our new Java API client expects us to get ID always, and if not, bum, an exception. The only way to work around this is to disable the property check this way. It looks kind of scary, right? Okay, now, if you use your entity ID is Elasticsearch ID, you have a choice. You can retrieve it using either ID of stored fields or doc values field. And doc values work better on the Elasticsearch side. However, ID is better for our client, and overall the difference is negligible. But if this Elasticsearch performance is bottleneck, you know, it's better to use doc values. To recap, to optimize our search response, we use doc values to get just a few key fields and consider disabling stored fields. And now it's time for our last question, how to write to Elasticsearch. Some time ago, after we had stopped getting data from Elasticsearch, we decided to remove all unused fields. We removed a lot. The size of our storage almost halved. Do you think the search speed improved? Who thinks so? Please raise your hand. Okay, you get the point. Someone thinks it got worse? Yes, you know. Yes, indeed it didn't improve. Since we use doc values, Elasticsearch doesn't mess with redundant data. But the latency spikes got bigger. Which spikes? Here's our latency graph. As you can see, we always have some spikes here. I won't keep you guessing. It's all due to merges. Let's dive into it. Any new data we send to Elasticsearch first lands in its memory. Periodically, it gets flushed to disk, creating a new immutable segment. Each segment is like a mini index having its own storages, doc values, stored fields, everything, and caches and inverted indices. And now each shard consists of multiple segments. And you remember, the search is executed in one single thread. So, for search efficiency, the number of segments needs to be small. Hence, Elasticsearch now kicks off a merge and combines the data of two old segments to a new one. All is done in the separate thread and totally transparent to our searches. But doesn't it bug them? Here's our merge graph. Each spike here is merging of two or more segments. And now look at the Elasticsearch CPU usage graph. See those spikes matching the merges? And here's our latency graph again. Yes, it looks like Elasticsearch isn't a fan of all that hustle and bustle. Okay, we are short on time, so I'll quickly go over few optimizations that have worked for us. First, stop writing. Seriously, our mates from the advertisement team never update their storage, and that works like a charm. If you can't, increase flash period called refresh interval. Ours set to 5 minutes, and for large updates, we disabled it at all. That means we have fewer segments and fewer merges. Third, handle soft deletes. Since Elastic 6.5, deleted documents hang around for hours before vanishing and move from segment to segment with every merge. Really matters if you delete a lot like we do. This graph shows how introducing soft deletes increased our merge sizes, and the more documents moved, the harder the merge. These red spikes led to heavy freezes in our search requests. So we decided to disable it, but this parameter is deprecated, so it's better to adjust the retention lease period. And lastly, be mindful of how you set up your merges. By this QR code, you can find a nice article explaining merging configuration, but in any case, the best setup depends on many factors like index size, document size, many things. Change one, and the once optimal settings just don't work as well. That's exactly what happened when we removed fields from our documents. The size of each document decreased, but the number of documents moved increased. And you remember, the more documents moved, the harder the merge. So that's led to longer merge times, higher CPU usage, and bigger latency spikes. Sure, we fixed it. How? Tried and tested, and that's the main takeaway for today. Try and test. We optimized everything we could. All these steps together boosted our Elasticsearch performance. But what worked for us might not work for you. So experiment, optimize, test and measure everything, and then share your experiences. We'd like to hear about them. Thank you, everyone. Please send your feedbacks.